Heidi-ho, good neighbors. We are going to pick up here with the 4 different types of radioactive decay that can happen with nuclear decay in an atom. We're going to look at alpha decay, beta decay, gamma decay. We really like those Greek letters for some reason. And then positron emission. By the way, if you're curious about this picture here, this is a glow-in-the-dark watch dial, obviously. I don't know why the 6 isn't showing, but it's glow-in-the-dark because a lot of fancy, anyway, some of the cheaper ones don't do this, but fancier glow-in-the-dark watches, what they use to cause them to glow in the dark is actually tritium. It is a radioactive isotope of hydrogen, and it is glowing because of its radioactivity. It is not dangerous. I'm not saying throw away your glow-in-the-dark watches. I actually think it's really cool. Kind of wish I had one. Anyway, let's pick up here with alpha decay. So what alpha decay is the loss of an alpha particle. Who'd have thunk it? We are super original in how we name stuff, which is actually kind of nice that we're not so original because it makes it easy to remember. So alpha decay is the loss of 2 protons and 2 neutrons from the nucleus of an atom. Those 2 protons and 2 neutrons are what we call an alpha particle. That is also the helium nucleus, by the way. If you go back and look at helium and and its atomic number and molar mass, or atomic mass on the table, you'll see that helium has 4 as its atomic mass, and it has 2 protons. So helium is just, its nucleus anyways, 2 protons and 2 neutrons. This has no electrons, so it is not a helium atom that is leaving the nucleus. It is just a helium nucleus that is leaving the, whatever it is, the radioactive isotope. When we're reading these, by the way, just to remind you, because I know we've looked at these, oh boy, just a couple months ago now. We looked at atomic symbols like that, just to remind you of how to read those things. The big thing in the middle there is the chemical symbol. Up in the top left is the mass number, and in the bottom left is the atomic number. And so again, the atomic number is the number of protons, and the mass number is the protons plus the neutrons. So it's the protons and neutrons added together. So again, for the helium here, there's 4 protons and neutrons. 2 of them are protons, and so therefore we must have 2 neutrons as well. So it's the same type of thing here when we're looking at uranium-238, which is the same, or is the most common form of uranium, is 238. The 238 is the number of protons and neutrons added together. 92 of that 238 is protons. And that will always be true of uranium. Uranium is always going to have 92 protons. So a very common radioactive decay that happens because there's so much uranium-238 is uranium-238 turning into thorium-234 and giving off that alpha particle. Sometimes, by the way, and I don't remember if we're going to do that here or not. I don't see one there. Sometimes you might see this instead of the helium. That is just the symbol alpha, and so sometimes people will put that in there instead of helium just because it's not truly helium because it has no electrons, but it does mean the same thing. So either 4-2 with helium or 4-2 with the alpha symbol there, it is the same thing. They're both talking about the same thing. So anytime we have alpha decay, we are always going to have one of these as our one of our products, and just one. In reality, sometimes you do have more than one that is released, but for our purposes, we are only ever going to have one of these released. So if I tell you that you have uranium-238 and it's undergoing alpha decay, you know uranium-238 is your starting point. One of your products has to be helium, 4 and 2, and so just using math, we can figure out that third part, which is what we're going to do here in example 17.1. So let me put that up here. So uranium, or sorry, not uranium. It tells us to write the nuclear equation for the alpha decay of radon-224. So we have radon, which is Ra, and the 224 there, if it gives you the symbol and then a number, the number is always the mass number. So we need the other one as well. We need the atomic number. If you go to the periodic table and you look for, oh sorry, I said radon. That's actually radium. So radium is number 88. Again, I get those two mixed up all the time. Radium is number 88, and it's Ra. Radon is number 86, and it is Rn. I get those mixed up all the time, unfortunately. So we have this, and it is undergoing alpha decay, and the question wants us to write the equation for that. So anytime we are writing a nuclear equation, or nuclear decay, we're only ever going to have one reactant. We have some starting material, and the very nature of nuclear decay is that you have something that is breaking apart. That is always going to be the case. So we're only ever going to have one of these. And so because we know that we're undergoing alpha decay, we also know that one of our daughter nuclides, as they're called, the things that are produced here, is going to be the helium-4, 2, which is the helium nucleus. So to find that third one, we can just use the law of conservation of mass. If we started with 88 protons, we didn't lose any protons here. We didn't turn protons into something else. We have to have the same atomic number on the left as we have on the right. And that will always be the case for all the things that we're looking at. We actually will see some situations where we do turn protons into other things here in just a minute, or turn other things into protons. But we'll still always be able to see that the atomic number on the left is going to be equal to the atomic number on the right. So if we had 88 to start off with on the left here, on the right side, we are going to have 86 as our atomic number. Same thing with the mass number. We started with 224, 4 of those left with the helium, and so we are going to have 220. And if we go and look at the periodic table, number 86 is radon. That's right, we're just talking about that actually. All right. So hopefully that makes sense. Anytime we're doing an alpha decay, this is always one of the products. And with any of the nuclear equations we're going to be looking at, the mass numbers on both sides must add up to be the same, and the atomic numbers on both sides must add up to be the same. All right, one last thing here about alpha radiation. Alpha radiation is actually the most dangerous kind of radiation if it gets to you. If it can get to your cells, if it can get to your DNA, it is very, very bad. The flip side to that is because it is so energetic, because the particles are so large, they can't travel very far. It's actually very, very easy to shield yourself from alpha radiation. You could have an alpha source a foot away from you, and the amount of radiation that would be getting to you, unless it was a very powerful alpha source, the amount of radiation getting to you would be dramatically less compared to if you were right up next to it, simply because the atmosphere can shield you from alpha radiation. Again, just because the particles are so big, as those helium nuclei are zipping through space, they bump into the nitrogen and oxygen and other stuff in the atmosphere, and they lose a lot of their energy. So if you put a piece of paper between you and the alpha source, you're going to be pretty much safe at that point. Not that I would suggest doing it, getting that close to a powerful alpha source, but it is fairly easy to protect yourself. The one situation where this doesn't, there's not really a good way to protect yourself is if you get some of it inside you, if you digest it, if you internalize the alpha source. This is actually a very common method for political assassinations by certain countries whose name shall not be spoken. There are certain countries who favor poisoning political dissidents and other people with radioactive isotopes of polonium, I believe. They put it into their into people's tea and things like that, and so then when they drink the tea, now the radioactive isotope, which, you know, if you had a piece of paper between you and it, would be relatively harmless, but now you have ingested it, and it is inside your digestive tract, and it is really messing you up, and you usually die fairly quickly from something like that. So don't digest the alpha sources. Alright, let's do one more real quick. I was hoping to get through all these, but I think I'm moving a little bit slow to do all these in one video. So we'll do beta radiation, then we'll call it for this one. So beta decay is the release of beta radiation. Again, we're super original in how we name stuff. And what a beta particle is, which is the thing that's being released by beta decay, is a very high energy electron. And it is the exact same particle as an electron. It is, in fact, just an electron. But it is extremely high energy. It's much more energetic than just, you know, all the electrons that are inside you right now. Because it is just blasted out of that nucleus at a really, really high rate of speed. So it is more dangerous than the average electron, but it is just an electron. And what happens in the nucleus is, because there are no electrons in here, if you remember, there are no electrons in the nucleus. So when the nucleus spits an electron out, it is losing negative charge. That negative charge had to come from somewhere, and where it comes from is one of the neutrons in the nucleus. So there's a neutron in the nucleus that, when the nucleus undergoes beta radiation, or it undergoes beta decay, that neutron actually turns into a proton. So that neutron spits the electron out, and as a result of losing that electron, it becomes a proton. Because you can't just have a positively charged neutron. That's not a thing. It actually literally becomes a proton. And so when we have equations where we're trying to describe what's happening here, what we use for the electron is this symbol here. We use an E to represent the electron. It has no mass in terms of having protons or neutrons, and so its mass number is 0. But it, even though it doesn't have a proton, again, normally we say that the atomic number down here is the number of protons. It does have the same charge as a proton, but opposite in sign. And so we go ahead and give it a -1 atomic number. And so if you notice here, what we said earlier is still holding true. We have 88 atomic numbers on the left side of this equation, and we still have 88 over here. It's just we have 89 and a -1, which when you add those together gives you 88. So we started with 88 protons. Because we turned a neutron into a proton, we now have 89 protons, which is actinium. So radium gets turned into actinium. Notice that the mass number does not change. And that's also going to be true for all the rest of the types of radiation we're going to see for the rest of this chapter. The only type of decay that changes the mass number is alpha decay. Beta decay, positron emission, and gamma decay or gamma radiation. None of those change the mass number. The only thing that changes the mass number is alpha decay. Okay, so let's do a quick example here. Let me see, do I have a spot to do it? No. So we'll just do it right down here. So 17.2 is asking us to write the nuclear equation for the beta decay of berkelium, which is BK, 249. So we have berkelium 249. Berkelium, if you look at it on the periodic table, is, see, it's way down at the bottom. It's number 97. That's its atomic number. Because we're told that it's undergoing beta decay, we know one of the products is going to be this. No matter what is decaying, no matter what it decays into, one of the products is going to be a beta particle. Otherwise, it's not beta decay. So it has to be, this has to be one of the products. So then, all we have to do is work out what these other two numbers must be, based on the simple algebra here. So if we started with 97 atomic numbers on the left, we need 97 on the right. Since we have a -1 here, that means this has to be 98. We gained a proton, and the mass number is not going to change. And so if we look at the periodic table, element number 98, I believe, is californium. Yes, californium, CF. And that is the nuclear equation for the beta decay of berkelium. Berkelium, by the way, just FYI, named after Berkeley, California. Californium, as the name so subtly tells you, is named after California. So we have one element named after a thing in California turning into another element named after the state of California. So it's kind of cool. Alright, I think we'll call it there for this video, and I'll see you all in the next one.